right, we're back at the whiteboard. We haven't done this in a long time. I put this up on the back of my whiteboard. It's probably been up, close to a year, and I decided I ought to do something with it. So basically, you can hopefully see in here that this is a brain starting down here. Top of the spinal cord, brainstem coming up to the big cortex of the brain. It's very busy, and we're going to try to grind through it. But the big thing that I'm really trying to get to with this is understanding how human beings operate, and for me, the neuroscience, I wouldn't say it's necessarily my favorite piece of this. I'm kind of enamored at where the environment meets the genome at the level of the cell, and how that determines the coding and the transcription of our DNA to RNA to peptides and intercellular signaling and things like that. And this is just on a kind of a much bigger level. But ultimately, I want to get to this idea of the sapiocortex. And people have kind of asked me, I use the term all the time, what is that? And I found that we're kind of missing the ability to define what's really unique about human beings. And the human species is about 2 million years old, but Homo sapiens, us, and with this relatively new expansion of the cerebral cortex, the neocortex, we don't understand how that operates very well. So for me, the sapiocortex is the newest evolution of the neo, or the new cortex, okay? So it is distinct to Homo sapiens, really, and it is the reason that we have sort of broad, tall, foreheads and awkward heads, awkward to get them through a birth canal, and, kind of awkward in general. It is the part of a human being that has made us, because we're kind of awkward, right? We're kind of wimpy. We're not very strong. We're not very fast. So this is the part of a human being that has made us the apex species on the planet, right? It's allowed us to, build airplanes and rocket ships and sort of cosmic telescopes and things like that. But it's also the part of Homo sapiens, the last remaining human species, right? It's also part of Homo sapiens that makes us the apex predator on the planet, that we can, build bombs and nuclear weapons, and ultimately, potentially destroy our own home, the Earth, and destroy our own species. So the sapiocortex, like all new technology, it's a very advanced technology. It's a double-edged sword. It can be used for things that create safety in the world and to the benefit of human beings and the planet, or it can be used to create threat and danger in the world and to the detriment of the planet and all its species. But weirdly, most species are trying. The main purpose of every species, maybe the solitary purpose of every species, is to protect and propagate the genetic code. And human beings are kind of failing to do this at this moment in our evolution. We're creating more threat and danger in the world and making the planet sicker, other species sicker, and we're making ourselves sicker at the same time. So it's really important, and we do understand, how things, like airplanes fly, and how, satellites work, and how these advanced telescopes work and how to create, you know, particle accelerators and blow up micro stuff and, you know, sort of quantum mechanics and all that, you know, all that kind of stuff. Maybe we don't quite understand quantum mechanics yet, but we still haven't figured out how human beings actually operate, and that's a little bit problematic. Okay, enough of that. So let's just dig in right here and look at the brainstem coming up. This is where the sensory nerves come up from our limbs, through our spinal cord, up the spinal cord, you know, to reach the upper brain stem, and then the subcortical brain, and eventually get to the cortical brain, okay? And then at the level of the medulla, the pons, the midbrain, we have all these cranial nerves coming in to bring other sensations in. So we're talking about temperature, pressure, hot, sharp, dull, all that kind of stuff coming up from the bottom. But up in this part of the brainstem, we're talking about, well, smell's way up here, but in general, sight and sound and taste and all that kind of stuff is coming in. So this is the external environment coming into our brain and giving us information that will come up to our cortex, okay? That's important to note. And I think also when we're down here in the medulla, well, let's go down the brainstem. These three dots, those are sympathetic ganglion. So the sympathetic nervous system, and so we're talking about kind of the fight or flight response there in those that are running outside the spinal cord, but at the level of the spinal cord. And then embedded in the medulla are the nuclei, the dorsal motor nucleus, the nucleus tractus solitarius, and the nucleus ambiguus of the vagus nerve, our parasympathetic system, more of our breathe and feed, kind of rest, relax part of our nervous system. So information coming in from our environment, that gets to the level of the medulla, we're already reflexively acting on that information to have an appropriate physiologic response for the demands of the moment, whether we're exercising or playing, or if we're fighting or fleeing, or if we're in a time where we're connecting with other people, having a meal, socializing. That all can, be modified at this very low primitive level. We come up here to the pons and the cerebellum, again, more reflex type activity. Maybe there's a little bit of cognitive type stuff that happens in the cerebellum, but older brain, kind of almost like a mini brain to us back there. And then we get up to the midbrain, and this little black area is the periaqueductal gray. So this information's coming in from the environment, and it's, flipping our physiology, and there's this flow of sort of data coming up to the midbrain at the periaqueductal gray. And we're already kind of there, also starting to make some almost decisions or priority, not cognitive decisions, but physiologic decisions at this level. And the periaqueductal gray does stuff like it amplifies signaling. So if there's something out there that we really need to pay attention to in the environment, periaqueductal gray is going to amplify the signaling. And it has some particularly interesting roles in pain, right? And particularly in chronic pain, where the chronic amplification of pain signaling, even without any tissue injury, without any real hurt or harm going on, signaling is over-amplified. But if you think about, people with, fibromyalgia or migraine headaches or things like that, they have amplification, not just of pain, but amplification of other signals. Bright lights are too bright, right? Sound is too loud. All of these types of things that get amplified right at the midbrain that create a hypersensitivity syndrome when our system is loaded with threat, right? Okay, so then you're going to see a little cluster of nuclei up here in the midbrain too, okay? And those are reservoirs of neurotransmitters. And I always like to point out that neurotransmitters are neurotransmitters here, right? But the same monoamine type molecules are also transmitters, maybe not even neurotransmitter, intercellular transmitters at an intracellular level throughout the body. But in the brain, we do have big reservoirs of these neurotransmitters, and the substantia nigra is not so important to this discussion, but it's full of dopamine. The ventral tegmentum, full of dopamine. The locus cerealis, full of noradrenaline or norepinephrine if you prefer. And the raphe nuclei, kind of running up and down the brainstem, have serotonin, 5-HT, okay? So as the signaling comes in from the environment telling us what's going on, it's gonna, flip switches, and these neurotransmitters, these monoamine neurotransmitters, are going to be pushed up to the cerebral cortex in kind of this fashion. So this is very reflex physiology, neurosignaling, but the whole physiologic soup that's running through our body, of which these monoamines are part of that soup. And they come up through what's called the striatum, and from the striatum, they eventually reach sort of the older cortex and then get up to our newer cortex. And that flow becomes, significant in a little bit. Like, for example, here, the nucleus accumbens, in some ways, is kind of the tip of this striatal flow. And it integrates with the frontal lobe and, the entire system, but particularly with the frontal lobe. And it's full of dopamine transmission. So dopamine transmission really has to do with motion, right? Has to do with movement, has to do with motivation. So that's part of what's going here. It has to do with our behavior, but it also has to do with how we feel, what our emotions are, and it has to do also, when it kind of gets up into here, what our thoughts are, what kind of thoughts are coming up to our head. And the interplay between some of these structures in the cortex is very, very interesting. I should also add that this flow and the nucleus accumbens, they also have to do a little bit of assessment with risk and reward. And if we get reward, it's reinforced. We want to do it again, kind of thing. And so it can become very involved in addictions, particularly if we are seeking out a life where we think that, we want to avoid pain and seek pleasure. Bad paradigm, right? We can fall into some significant addiction issues. Okay, so now we've gotten essentially to the midbrain, and we're sitting right here in this brown kind of beigey blob. At the top of that is the thalamus. And the thalamus is a relay station for sensory information. So we got all this information coming in from the exterior that the thalamus is already kind of making some non-cognitive, but some decisions about what needs to be prioritized. Where am I sending this? I'm going to relay it out to the system. Is there danger near? Do I need to activate kind of the limbic system? Things like that. So the thalamus is a sensory relay station, but it's processing the information. It's processing that data. And it also takes from the inside back down some information, from inside of our body, of what's going on in the body, and disseminates that as well. So that's, what we talk exteroception, all this data coming in from the outside world, and then interoception, what's going on in our body, in our fascia, in our viscera, from our brain, the relaying of that type of information upstream to the rest of the brain. All right. Then we have other sort of subcortical structures that are worth mentioning. So let's go to the hypothalamus. So kind of below, a little bit in front of the thalamus is the hypothalamus, and the hypothalamus is involved in a lot of neurohormonal signaling. So both sort of neurologic type peptides, oxytocin, vasopressin type stuff. One safety kind of signaler, one threat kind of signaler, but also hormones, stress hormones. And so the hypothalamus goes to the pituitary and eventually it communicates to the adrenal gland for the production of cortical adrenal hormone or cortisol, and the production of the other major adrenal hormone, which is adrenaline. So again, we've got fight or flight stuff here signaling through the blood. It's not as fast as the fight or flight signaling that goes through the autonomics, through the parasympathetics and the sympathetics, but it's pretty fast. So these things are important to us because we are a multicellular, in fact, differentiated cellular organism. We're fairly big, and we have to communicate the status. We have to communicate this information, the status, across this large organism, and it benefits us to do it relatively fast. So we can do it with nerve transmission, but we can also dump things into the blood, and through vascular circulation, we can communicate the status of the greater system, and activate a fight or flight response type thing. But I will add that those two things, the autonomics and these hormones, they're really, kind of conceptually, are about a century old. So that's just something to think about. We still operate in that model. It's not wrong, it is correct, but it's not the complete story. And we have so much more going on at a cellular level, at a genomic level, that really has not been incorporated into sort of our threat and safety responses in the modern paradigm yet. Okay, so then other subcortical structures, we have the hippocampus here, which is, it plays a role in, it's in the temporal lobe, subcortical, playing a role in memory and integrating emotions and the subcortical kind of structures. So it wraps around from the kind of the medial temporal lobe like a seahorse, comes more to the front and communicates with the hypothalamus, but also with the amygdala, okay? So the amygdala, we tend to think of it as, our alarm system, danger's near. It's really primarily one nucleus in the amygdala, but it lights up, the whole threat response, activating certain parts of the brain, participating in the deactivation of other parts of the brain, and kind of signaling this whole alarm system to get going from a subcortical level. We can have danger near and have all this stuff going on right here, and we aren't yet even aware of it at a cortical level. Awareness comes at the cortical level. So let's bump up a little further here. Kind of at the next level is sort of the older cortex, and so we have the parahippocampal cortex that kind of wraps around the hippocampus, and then we have the cingulate cortex here, with the anterior cingulate cortex here, has significant roles in decision making, connections, social connections, and other connections, and also with the generation of conflict and an associated threat response. And then in the posterior aspect of the cingulate gyrus, we tend to think a little bit more about the default mode network and self-contemplation and sort of concern with the self, and development of things like ruminations, even depression and things like that back here. And then we have sort of this arc here that is sort of our more primitive motivation cortex, up in here. And again, the striatum is feeding up this way, and then it, feeding up to the motor cortex. So this is kind of an older flow, right? It still exists in us, but in certain mammals, the brain kind of cuts off here. You can look at their skulls, right? All this stuff isn't out here, so this is sort of primitive flow, cingulate gyrus, motivation, motor cortex, motion, movement, motivation, kind of all that kind of stuff flowing through there. So that's what I would tend to call the paleocortex. It's older, and then we get out here into what is typically referred to as the neocortex, a little bit more prefrontal cortex, and kind of in front of the motor functions of the brain. That most mammals have a neocortex, and then on the back side here, this is a lot of our sensory information with sensory integration on the posterior aspect, the parietal, occipital lobe, the posterior temporal lobe back in there. Okay, so that kind of brings us all the way up, to the cortex. So we've got the ventral prefrontal cortex, right? We've got the dorsal prefrontal cortex. We have sort of our motor area and our motor association areas. We have our somatosensory area where we're sensing the temperature and pressure and sharpness, things like that up in here with the sensory association areas. And then we come back, sort of off the parietal lobe to the occipital lobe, our visual cortex, and then kind of wrapping back into our temporal lobe where we have our auditory cortex. Sort of sensory stuff here, motor stuff more here in the dynamic of the brain. So now let's go on and talk a little bit more kind of about the sapiocortex, the neocortex, of which, the newest of the new brain, right? So it involves the prefrontal cortex. It involves some of the temporal cortex. It involves some of the parietal cortex. And interestingly, this is all newer brain in general, but the parts of what I would consider more paleocortex, the older, deeper cortex of the brain, the cingulate cortex that we just talked about, the anterior cingulate cortex had also expanded with the prefrontal cortex, and it's relatively new, okay? And the anterior insular cortex also expanded with the neocortex. And the insula is this sort of black, hard to see area in the brain. You literally have to open up the lateral fissure, kind of get between the temporal, frontal kind of parietal crease there, and the insula is deep in the brain. But it interestingly, as a paleo, an older cortical structure in the brain, had an expansion with the development of the sapiocortex that has some significance. So a lot of times when we're talking about, human neocortex, we tend to just focus on the prefrontal cortex evolution, but it was really, the prefrontal expansion, probably first through the ventral area, and then as that expanded, if you just look at human skulls and their evolution, eventually expanding the dorsal part of the brain, kind of the area behind our eyeballs, gives us the high forehead. In association with that, we were getting some expansion in the precuneus here, part of the parietal lobe, and we had some interesting expansion in the anterior part of the cingulate cortex here, and in the anterior part of the insular cortex. So it was kind of, a lot of brain was expanding. Did I mention the expansion in the temporal cortex? There's sort of more lateral expansion than this vertical expansion in the temporal cortex, where very specific language functions are, right? We have a very unique way of performing symbolic communication, as well as developing narratives and stories. So that part expanded, but we also had another expansion more medially in the temporal cortex, where a lot of sort of declarative memory is the ability to play Jeopardy, right? Things like that are in that part of the sapiocortical expansion. Okay, so let's just review all of those real quickly. We're going to start with the lateral prefrontal cortex. It kind of has, there's a lot going on, but in a quick summary, it's responsible for ideation and constructs, okay? So we have a dorsal lateral prefrontal cortex, and our executive functions are in there. And that's, ability to reason, to contemplate, to create, to plan, to sequence things, judgment, things like that are in the dorsal lateral prefrontal cortex, okay? And that's probably the newest part of the overall brain, but where am I here? Yeah, we're gonna go ventral. I'm not finding my ventral, but anyway, here we go. So ventral prefrontal cortex, the lateral ventral prefrontal cortex is responsible for kind of our ability to imagine things and be able to visualize, see things, and start to put sort of symbolic meaning around what we see. So, very important that we can create, imagine things and create symbolism around that, because that was eventually the evolution of our very advanced symbolic communication system, language, right? Okay, so on the medial side of the dorsal prefrontal cortex, so dorsal medial prefrontal cortex, we have the inhibition of mental, cognitive information and behaviors. So this is the equivalent of sort of thought suppression or behavioral constraint. That tends to come through the dorsal medial prefrontal cortex. And then on the ventral medial prefrontal cortex, this is an area that's highly connected with our social emotional network, right? And being these sort of awkward, weak, slow animals, it's very important that we are well connected to the tribe. We can't survive individually very long, which has some implications for the modern day and our propensity to create conflict and destroy our ability to cooperate and adapt with each other. But anyway, the ventral medial prefrontal cortex also is responsible for social emotional inhibition. Okay, so it makes sense that the mental, our smartest IQ part, is up dorsally, and behaviors are up dorsally too. Motor movement here. So these guys, we're going to suppress or constrain those, and then our emotional network comes through underneath that to the frontal area. And so we're going to have the ventral medial part is inhibitory, and that's repression, right? Which can really make us sick if we repress it. So let's just talk about how functionally that kind of looks. We've got all this information coming in from below, from the environment, and some information coming in, from our guts, from the fascia, the viscera, and our even our emotional status, kind of our gut feelings, that are all kind of coming in to a central point, and that physiology wants to flow forward. And without the sapiocortex in many animals and many mammals, this kind of just flows through into instinctive behavior, right? You get an emotional feeling, you get an instinctive behavior that just kind of comes out, you know, maybe my dog has some thoughts like I'd like water now, you know, something like that coming through. But what can happen within the human brain, within particularly a very socially aware human brain, is as this natural flow of physiology is coming forward, right? The medial prefrontal cortex, both dorsal and ventral, can basically take this physiologic flow and say, nah, we're not doing that, you know. And so you've got a bottom-up flow and then top-down flow, and they're doing this with each other. They're kind of pounding into each other. Which one's gonna win? Now, if we're in enough, you know, threat and we get pissed off, this part of the brain goes offline. That flow comes through, right? But you know, a lot of our lives, we chronically we tend to spend it with all of the must-have, shoulds. You know, those type of social cultural rules pounding back on our natural physiologic flow. So when that happens, right? When that happens, when we get this friction point, it registers in the anterior cingulate cortex. The anterior cingulate cortex, at a primitive level, is where decisions are made, where connections happen, right? Social connections happen. But ultimately, conflict registers here in the anterior cingulate cortex. And that can be any kind of conflict, but this is almost an internal conflict between our natural physiologic flow as stimulated by the environment and then our sapiocortical functions that say, don't show that, don't do that, don't think that. To be a good human being, you need to, you know, all that kind of stuff. So when that registers as conflict in this area, the anterior cingulate cortex is highly connected to the limbic system, you know, down to the amygdala, and now we're in a threat response, okay? And a chronic threat response makes us sick. So a chronic threat response is inflammatory and catabolic. It deteriorates our tissues. It degenerates our tissues. It's catabolic for a reason. We need fuel in a fight or flight from a tiger, right? But we take a lot of that fuel, because if you're running from a tiger, you can't stop at McDonald's to get a hamburger, right? So when we're running from the tiger, we need fuel, and where we prioritize getting that fuel, it is from our own tissues. So chronic threat, being chased by a tiger chronically, leads to chronic inflammation and degenerative diseases. And think about how many, you know, probably 80% of everything we see in medicine comes into that category. Okay, so we kind of got through that. Let's go down here and, well, we'll make one more comment here, that the lateral prefrontal cortex is involved in ideation and constructs. The medial prefrontal cortex is involved in social kind of interactions and inhibitions in our social contracts there. You know, but there's an emotional piece to that as well. You know, it kind of houses our ability to be kind and compassionate and empathetic as well. Okay, and then as we talked about a little while ago, the lateral temporal lobe houses our symbolic communication, our language, both you know, kind of pushing into the ventral lateral area, the idea of symbolism, symbolic communication, language, but also when we get down into the lateral temporal lobe, this is where we start getting into the ability to create narratives, right? We can create these scenarios and have a fairly long narrative. Most of our life now has become narrative. I would argue we probably all talk too much, and I'm doing that right now, right? Everything we do, whether we're reading or watching a movie or on social media or hanging out with somebody, you know, it's all about the story. It's all about the narrative. And so let's come down here talk about the medial temporal lobe. We mentioned it briefly. Memory for events, declarative memory, names, facts, jeopardy. But we also embed stories in the medial temporal lobe. So we create the stories that we remember over time, and we tell them over and over again. A lot of them are victim, martyr, hero stories, right? So that's kind of that flow from you know, the dorsal cortex and into the ventral cortex, and coming back this way into the temporal lobe, where we can, you know, create some pretty amazing constructs, imagination, symbolism, language, narrative, story to tell over and over again, inescapable from our past, making it very difficult to be in the present moment kind of stuff. Okay, now the other piece of this that I think is important to conceptualize is that the insula, which did have an anterior expansion with the sapiocortex, the insula is where we have our interoception. If this area is our exteroception, right, the external environment, everything's going on there, the insula is what's going on inside of us. And so it's very interesting that our emotions register in the insula. So the physiology of emotion, right? When it hits the insula, it becomes a feeling. That becomes a feeling, right? And right beside it, the information coming up from our viscera, you know, from our guts, and coming up from our connective tissues, our fascia, also register here in the insula. Side by side, we have feelings that are our emotions, and our visceral feelings, and even our fascial feelings are all sitting right there side by side. And that's referred to as our interoception, okay? And in this scenario of you know, imagination, constructs, symbolism, narrative, stories, we can embed a belief. And because that belief is here in the gut, in this primitive brain, you know, it registers as a gut feeling, almost like an instinct. It doesn't necessarily have to be real, be reality, be, you know, dorsal lateral prefrontal cortex kind of rational thought stuff. It's just a gut feeling. And we just know things to be true based on our gut feeling. And it's powerful to have those gut feelings, but they can register as beliefs that are completely without reality. And that's a major problem that I'm going to come back to in a second here. Okay, let's just kind of finish up on the back side here a little bit. And so we've got our somatosensory cortex feeding the sensory association area with the external information, and then we have our internal information that's registering in the insula. All of those are our feelings. Some are somatosensory feelings, some are emotional, visceral, fascial sensations, okay? I want to comment here on the precuneus. This is the anterior part of the precuneus is really important to the integration of our environment, both intro environment and extero environment, integrating our environment with a sense of self, okay? And some people call it, you know, feeling embodied. So when we're in threat, deep chronic threat, right, we can sort of become disembodied, I guess, is that the right term? We lose our sense of embodiment and we become numb. You know, all of these sensations get diminished, and frequently people in deep stages of chronic threat complain of just feeling numb. Sometimes it feels better than being anxious to them. But also, on a psychedelic or in a moment of awe, we can also lose the sense of self and have this sense of profound connection with the environment around us. And so this is a very interesting location here. And it also is part of the default mode network, which is implicated in states of depression and self-obsession and rumination and things like that. So I just want to bring that in because it did have an expansion within the sapiocortex. And for our purposes right now, we just want to think of this as sort of an integrating place for all of the data that's coming in to integrate it into our sense of self. Okay? Now, with that in mind, the insula seems to be perhaps the place where we integrate the false self, okay? Where we integrate maybe something along the lines of perhaps an ego, where we can take a bubble up thought and create an idea and then put that into a construct and use our imagination to play with it, turn it into something symbolic and push it into a narrative, push it into a story to be remembered, and impregnate our brain with a belief about who we are, in the world that is not really based in reality. It's a construct that fits the social cultural environment typically, and it's a sense of our ego. We use illusion of control techniques to protect this false self that we've evolved and believe in, that kind of exists in that area of gut feelings. And so that's interesting, and it's sort of the location from the integration of something that here would be like the real self at the core, and then the false self that surrounds the real self within this part of the brain, and kind of prevents us from realizing the real self because we're stuck in this socio-cultural construct of what we need to be in society. And not only that, what we need to do to protect what we believe we need to be in society. So what we need to do to protect the false self, when really our concern should be with what we need to do to protect the real self. So keep that in mind here. Okay, so let's get back to threat versus safety. When we are running from the tiger, this is acute threat, not chronic threat. And we essentially evolved over about 4.2 billion years. Humans, have been around for about 2 million years. Homo sapiens for 250, 300,000 years, not very long. So the vast majority of our evolution is in response to physical threats in the environment. A toxin, a tiger, a pathogen, so I like to say pathogens and predators, but we have to throw toxins in there as well. And so our response to threat is largely geared around responding to those physical threats. And it isn't so much geared to what we experience today. We can run the threat list: generational threat, historical threat, physical threat, emotional threat, social threat, behavioral threats, mental threats, societal threats, financial threats, spiritual threats, sort of existential threat type stuff. So it's a long list. Of only a fraction of that list is actually physical threats, but our system is always responding to physical threats. So when we're running from the tiger, it isn't a time to be in our dorsolateral prefrontal cortex, doing calculus, right? It isn't a good time to be in a state of imagination. We need to be more focused on the external environment, okay? It isn't a time to focus on connection and bonding. The tiger is not interested in connection and bonding with us. He's interested in eating us, okay? So our symbolic communication system is irrelevant. You know, we can't sit down and have a conversation with a tiger and rationalize with the tiger why it shouldn't eat us. It's not a good time for creating narratives or telling stories. And in this moment, that false self, you know, that constructed self is pretty irrelevant to us. And, you know, back here, we're going to be focused on self-protection based on the environmental input. So what ends up happening is the parts of the brain that are going to help us deal with a toxin, kill a pathogen, escape from a predator, perhaps kill a predator, those parts of our brain are online. And it's not the sapiocortex. The sapiocortex is pretty useless in that environment. So we downregulate it, and we have a number of ways of downregulating it. We can do it through peptide signaling, we can do it through monoamine signaling, we can do it through neurotransmission, we can do it through blood flow. All of these things that involve the sapiocortex get downregulated in that moment, okay? So what we have to now contemplate about that phenomenon is that our IQ is lower, our EQ is lower, and we're tending to operate in this paleocortex, subcortical, you know, autonomic nervous system, and we change phenotypically, right? We're very different when we can't think, we can't contemplate, we can't be rational, we can't connect and bond, you know. And people will look at this, when we have chronic threat, we have these same things going on chronically. So in chronic threat, we tend to be antisocial, you know, anxious, asocial, depressed, maybe in despair, maybe numb, right? And a lot of the antisocial behaviors we would describe as bad, right? As evil. And then all of our sort of brilliance and social connection we describe as good and moral. It's really not, it's not good or bad. It's simply threat or safety. And the environment, right, coming in, telling us we're in threat or we're safe, determines whether or not we're, quote, good or bad or evil or moral, right? So that's something that needs contemplation for the world today, because it has implications in all the facets of our life. In healthcare, we have to understand the catabolic and degenerative inflammatory aspects of being in chronic threat. But we also have to understand when we're seeing antisocial criminal behavior, doubling down on threat isn't going to fix that. It's going to make it worse. And we're seeing that, you know, really across the globe, but particularly in the United States right now. So the next piece of this that is of concern is, over a long time of chronic threat, our bodies not only downregulate, but they start undergoing a process of deconstruction. So we can see the sapiocortex undergo deconstruction. And eventually it can undergo destruction and massive rapid degeneration. And that's where we get into a lot of our neurodegenerative kind of diseases is, you know, probably the classic one would be Alzheimer's, where a lot of these functions, you know, the dorsolateral prefrontal functions, the cognitive strength goes away, the ability to connect and bond goes away, right? Language gets, you know, kind of sparse and difficult, can't find words. And memory, right, medial temporal lobe stuff, really takes a hit. Parahippocampus, which is not only the hippocampus, but parahippocampus and the medial temporal lobes have a lot of atrophy in them in that. But that's, a neurologic condition, but it's almost identical for schizophrenia, which we can tend to consider a psychological condition. Schizophrenia is also a neurodegenerative disorder. And what else gets lost, right? We start losing the sense of self. We lose sensory integration. Remember, this is part of the neocortex too, and a piece of it is part of the sapiocortex. And when we start to lose that, when we start to really lose a sense of ourselves and reality, then you start seeing sort of delusions, erratic thinking, hallucinations, that, maybe psilocybin sort of frees this up, and we have some dissociation from self in a state of safety that is enlightening, but in Parkinson's and Alzheimer's and schizophrenia, that's not what we're seeing here. We're seeing the degeneration, the loss of connectivity, not an expansive connectivity within the brain and to the environment. And so we see all those aspects. And what's driving it? Chronic threat. Arguably, your threat load accumulates over a lifetime. So, if you can't dissipate it, so age is the biggest risk factor for everything. So we can say maybe, chronology or age plus threat load is when we're going to see this kind of degeneration more. And Parkinson's a little bit unique because the Parkinson's tends to go a little deeper, right? Not only are you getting sort of this neocortical, sapiocortical degeneration, but that it replicates a deeper state of threat, not sort of the anger and anxiety state, but where the monoamine neurotransmitters get depleted, particularly dopamine, and we're really going into a hiding response, right? Parkinson's patients, they can't move, they can barely speak. What's better to hide? Don't move, don't make any noise, right? And then they start curling, they get kyphotic and curl into more and more of a fetal position. Their blood pressure drops out from them. It's telling them, get down on the ground, lie down, pretend you're dead, right? That's kind of the process of Parkinson's neurodegeneration. So it's getting all the way down into these, subcortical structures of the brain and having an effect there as well. So, got to wrap this up because it's gone on too long, too much narrative, hopefully not too much belief, a lot of construct, right? But I think that the bottom line here is we have to understand the sapiocortex. We have to understand kind of how our brain functions, communicates with itself and the greater organism to be able to counter some of these processes without the awareness that we're doing all these, that our body, we're in less control. We think we're in control when we talk about a self. We have this sense of somebody as a pilot behind our eyeballs somewhere who's in control of the entire world, when in fact 99% of what's going on, and maybe more in the world, and certainly, probably 99% of everything that's going on in our body is completely out of our control. We have a small locus of control. We have a small locus of being able to determine outcome and things like that. There are many other factors that are involved in how we present to the world, what phenotype we show up with, whether we're smart and connected or disconnected and not so smart and antisocial. And we have to understand that in kind of a societal construct. And we got to understand that, in terms of global dynamics as well. But we have to understand that in terms of our overall health, and things like attention deficit disorder, autism, post-traumatic stress disorder, schizophrenia, anxiety, depression, despair, all of those things that eventually can go into neurodegenerative type diseases. And we also have to understand it in terms of the false self and the illusions of control we create, which evolve into our personality, sort of, and they also evolve into our personality disorders. So it's a sort of this global understanding of the total physiology and then neurophysiology of the brain, and specifically what is unique to us, the sapiocortex, and how the sapiocortex makes us the apex species on the planet and also the apex predator on the planet. And finally, how it cuts both ways, not only for the planet and every species on the planet, for us as well, and that we, unlike any other species, have the potential to create our own annihilation and extinction. I'll leave it at that.